Good day and welcome to One-on-One Math Private Tutors. Today we are looking at O-Level and IGCSE Computer Science. We continue with the topic Methods of Error Detection. Today we are going to look at checksum and echo-check and describe how check digit is used to detect errors in data entry and identify examples of when a check digit is used, including International Standard Book Number, ISBN, and barcodes. We are also going to describe how an automatic repeat query or ARQ can be used to establish that data is received without error. We are also going to use positive and negative acknowledgements and timeouts. Checksum. A checksum is a method used to check if data has been changed or corrupted following data transmission. Data is sent in blocks, and an additional value called the checksum is sent at the end of the block of data. The checksum process is as follows. When a block of data is about to be transmitted, the checksum is calculated from the block of data. The calculation is done using an agreed algorithm. This algorithm has been agreed by the sender and the receiver. The checksum is then transmitted with the block of data. At the receiving end, the checksum is recalculated by the computer using the block of data. The agreed algorithm is used to find the checksum. The recalculated checksum is then compared to the checksum sent with the data block. If the two checksums are the same, then no transmission errors have occurred. Otherwise, a request is made to resend the block of data. Echo check. With echo check, when data is sent to another device, this data is sent back again to the sender. The sender's computer compares the two sets of data to check if any errors occurred during the transmission process. This method isn't very reliable if the two sets of data are different. It cannot be known whether the error occurred when sending the data in the first place or if the error occurred when sending the data back for checking. So if we have a sender and a receiver, the data is sent to the receiver sends back the data, the sender compares the sent back data with the original data, but if there are errors, we don't know if the errors occurred when sending the data there or when the data is sent back. However, if no errors occurred, then it is another way to check that the data was transmitted correctly. So in summary, a copy of the data is sent back to the sender. The returned data is compared with the original data by the sender's computer. If there are no differences, then the data was sent without error. If the two sets of data are different, then an error occurred at some stage during the data transmission. So this is a diagrammatical representation of echo check. Data is sent from sender to receiver. The receiver returns data to the sender. Data is resent if any errors are found. Then we go to check digits. A check digit is the final digit included in a code. It is calculated from all the other digits in the code. Check digits are used for barcodes on products, such as International Standard Book Number, ISBN, and Vehicle Identification Numbers, VIN. Check digits are used to identify errors in data entry caused by mistyping or misscanning a barcode. they can usually detect the following types of error. An incorrect digit entered, for example, 5327 entered instead of 5307, where this digit has been entered incorrectly. Transposition errors, where two numbers have changed order, for example, 5037 instead of 5307. So these middle numbers have been transposed. Check digits can also be used to identify errors where omitted or extra digits, for example, 537 instead of 5307. So an omission has been made, or 53107 instead of 5307, an addition or extra digit here has been added. It can also be used to detect phonetic errors. For example, 13 instead of 30. There are a number of different methods used to generate a check digit. So we'll use this example of a barcode. This is ISBN 13 code with check digit. So these are the 13 digits of the barcode, with the first 12 digits being the digits of the barcode, and the last digit, the 9 here, is the check digit. We are going to see two methods we can use to generate this check digit from these 12 digits. There are a number of different methods used to generate a check digit. Two common methods will be considered here: ISBN 13 and modulo 11. The check digit in ISBN 13 is the 13th digit in the number. We will now consider two different calculations. The first calculation is the generation of the check digit. The second calculation is a verification of the check digit. That is a recalculation. Calculation 1. Generation of the check digit from the other 12 digits in a number. The following algorithm generates the check digit from the 12 other digits. The first step is add all the odd numbered digits together. So the odd digits are the first, the third, the fifth, the seventh, the ninth, and the 11th. So we add the odd numbered digits together, which is 9 plus 8 plus 3 plus 0 plus 8 plus 8, which will give us 36. This is the calculation shown. Then the next stage, add all the even numbered digits together and multiply the result by 3. So we'll say 3 times 7 plus 0 plus 4 plus 9 plus 3 plus 2, which will give us 75. Then we add the results from 1 and 2, which are these results, together and divide by 10. So 75 plus 36 will give us 111, divided by 10 will be 11, the remainder 1. Then we take the remainder. If it is 0, then use this value. Otherwise, subtract the remainder from 10 to find the check digit. So we say 10 minus 1, which will give us 9. So that will be our check digit. So we end up with the following 13-digit number, which matches the number shown in our barcode. So the first 12 digits are used to calculate the check digit. Now we go on to calculation 2, recalculating of the check digit from the 13-digit number, which now includes the check digit. To check that the ISBN 13-digit code is correct, including its check digit, a similar process is followed. So we add all the odd numbered digits together, including the check digit. So now, we'll say 9 plus 8 plus 3 plus 0 plus 8 plus 8 plus 9, which will give us 45. Then we add all the even number of digits together and multiply the result by 3. So it's 3 times 7 plus 0 plus 4 plus 9 plus 3 plus 2, which will give us 75. Then we add the results from this calculation, which is here. Then we get 120 and divide by 10. Divided by 10, which will give us 12, remainder 0. The number is correct if the remainder is 0. So here the remainder is 0. So the number is correct. So in the examination, you will not need to remember the steps shown in these algorithms. The steps will be given to you, but it is important that you understand how to use the algorithm to calculate or verify check digits. Example 2, the modulo 11. The modulo 11 can have varying lengths of numbers, which makes it suitable for many applications, such as product codes or vehicle identity numbers. The first calculation is the generation of the check digit. The second calculation is a verification of the check digit, that is a recalculation. Calculation 1, generation of the check digit from the other digits in a number. In this example, we will assume the original number contains only 7 digits. The following algorithm generates the check digit from the other 7 digits. Each digit in the number is given a weight of 8765432, starting from the left. Weightings start from 8, since the number will become 8-digit when the check digit is added. The digit is multiplied by its weight, and then each value is added to make a total. So if we have, for example, a 7-digit number of 4156710, the corresponding weights of these numbers are 8, 7, 6, 5, 4, 3, and 2. So we multiply each digit by the weight. 8 times 4, 32. 7 times 1, 7. 6 times 5, 30. 5 times 6, 30. 4 times 7, 28. 1 times 3, 3. 2 times 0 is 0. Then we add these results. After adding these results, we get a total of 130. We divide the total by 11, and we get 11, remainder 9. So we've divided the total by 11. The remainder is then subtracted from 11. So we say the remainder subtracted from 11, so 11 minus 9, which will give us 2. So we end up with an 8-digit number, including the check digit, which is our 2. So our number is this. Our 8-digit number is this, so we add a 2 in front of this 7-digit number. Now, we have to make a recalculation of the check digit from the 8-digit number, which now includes the check digit. So this is our second calculation to check that the 8-digit number is correct, including its check digit. We apply a similar process as follows. Each digit in the number is given a weight. Now the weight starts from 8 to 1. So this most significant number's weight is 8, and corresponding numbers will get 7, 6, up to 1. So this is 7, 6, 5, 4, 3, 2, and 1. Now, each digit is multiplied by its weighting, and then each value is added to make a total. So we say 8 times 4 is 32, plus 7 times 1, which is 7, plus 6 times 5, which is 30, plus 5 times 6, which is 30, plus 7 times 4, which is 28, plus 3 times 1, which is 3, plus 0 times 2, which is 0, plus 2 times 1, which is 3. This will give us a total of 132. Now the total is divided by 11. So we divide here by 11 to get 12, the remainder 0. The remainder is 0, therefore the number is correct. So if the remainder is 0, then the number, which is this one, is correct. So that is how we apply check digits. Now we go to automatic repeat requests, or ARQs. We have already considered parity checks and echo checks as a method to verify that data has arrived at its destination unchanged. An automatic repeat request, ARQ, is a third way used to check data following data transmission. This method can be best summarized as follows. ARQ uses positive and negative acknowledgements. These are messages sent to the receiver indicating that data has or has not been received correctly. They also use a timeout. This is the time interval allowed to elapse before an acknowledgement is received. The receiving device receives an error detection code as part of the data transmission. This is typically a cyclic redundancy check. This is used to detect whether the received data contains any transmission errors. If no error is detected, a positive acknowledgement is sent back to the sending device. However, if an error is detected, the receiving device now sends a negative acknowledgement to the sending device and requests retransmission of the data. A timeout is used by the sending device by waiting a predetermined amount of time. And if no acknowledgement of any type has been received by the sending device within this time limit, it automatically resends the data until positive acknowledgement is received, or until a predetermined number of retransmissions has taken place. Automatic repeat requests is often used by mobile phone networks to guarantee data integrity. Symmetric and asymmetric encryption. The purpose of encryption: when data is transmitted over any public network, wired or wireless, there is always a risk of it being intercepted by, for example, a hacker. Under these circumstances, a hacker is often referred to as an eavesdropper. Using encryption helps to minimize this risk. Encryption alters data in a form that is unreadable by anybody for whom the data is not intended. It cannot prevent the data being intercepted, but it stops it from making any sense to the eavesdropper. This is particularly important if the data is sensitive or confidential. For example, credit card or bank details, medical history, or legal documents. Plain text and ciphertext. The original data being sent is known as plain text. Once it has gone through an encryption algorithm, it produces ciphertext. Symmetric and asymmetric encryption. Symmetric encryption. Symmetric encryption uses an encryption key. The same key is used to encrypt and decrypt the encoded message. First of all, consider a simple system that uses a 10-digit binary encryption key and a decryption key. This gives 10 to the power 10 possible codes. Suppose our encryption key is this number, which means every letter in a word is shifted across the alphabet +4, +2, +9, +1, and so on. For example, the text computer science is exciting is our plain text. Now we use this encryption key to shift the letters. C is shifted 4 times, so we have C, D, E, F, G. In the alphabet, we shift it 1, 2, 3, 4 times. So C will be represented by G. O, P, Q, since we are shifting the second letter by 2, O moves 2 times to the right from O to Q. M is moved 9 times. So if we have M, N, O, P, Q, R, S, T. So we have 1, 2, 3, 4, 5, 6, 7, U, V, 8, 9. So we move 1, 2, 3, 4, 5, 6, 7, 8, 9. We shift it 9 times. So it is represented by V. For P, we move it 1 time, which is this one. P moves to Q. So P is represented by Q. Now, we do this using this key, 4291362856. Then we start again, 4291362856. Then we repeat again. So this plain text becomes encrypted to this ciphertext using this encryption key. So this is meaningless to whoever intercepts it. So to get back to the original message, it will be necessary to apply the same decryption key, that is 42913628, but in this case, the decryption process will be the reverse of encryption, and each letter will be shifted -4, -2, -9, -1, and so on. So that G becomes C, Q becomes O, and V becomes M, Q becomes P, and so on. However, modern computers could crack this encryption key in a matter of seconds. To try to combat this, we now use 256-bit encryption keys that give 2 to the power 256, or approximately 1.2 times 10 to the power 77 possible combination. And we must note, even this may not be enough as we head towards stronger quantum computers. The real difficulty is keeping the encryption key a secret. For example, it needs to be sent in an email or a text message, which cannot be intercepted. Therefore, the issue of security is always the main drawback of symmetrical encryption, since a single encryption key is required for both sender and recipient. Asymmetric encryption. Asymmetric encryption was developed to overcome the security problems associated with symmetric encryption. It makes use of two keys, called the public key and the private key. The public key is made available to everybody. The private key is only known to the computer user. Both types of key are needed to encrypt and decrypt messages. We will use an example to explain how this works. Suppose Tom and Jane work for the same company, and Tom wishes to send a confidential document to Jane. Jane uses an algorithm to generate a matching pair of keys, private and public, that they must keep stored on their computers. The matching pairs of keys are mathematically linked but can't be derived from each other. Jane now sends her public key to Tom. So Jane sends her public key to Tom. Tom now uses Jane's public key to encrypt the document he wishes to send to her, then sends his encrypted document, which is ciphertext, back to Jane. Jane uses her matching private key to unlock Tom's document and decrypt it. This works because the public key used to encrypt the document and the private key used to decrypt it are a matching pair generated on Jane's computer. Jane can't use the public key to decrypt the message. Jane can also exchange her public key with any number of people working in the company. So she is able to receive encrypted messages which have been encrypted using her public key, and she can then decrypt them using her matching private key. So this diagram shows that Jane can send her public key to anyone, but can only decrypt messages sent to her using her private key. However, if a two-way communication is required between all 5 workers, then they all need to generate their own matching public and private keys. Once this is done, all users then need to swap public keys so that they can send encrypted documents, files, and messages between each other. Each worker will then use their own private key to decrypt information being sent to them. With that, we come to the end of this section. Thank you.